This is the beginning of the projectiles section of kinematics, which makes up the main portion of this unit. It's also the most fun. So we're going to start off with a demonstration. Now let's graph what you just saw in that demonstration with the spring cannon. So here's our spring cannon. It's got a spring in it. It just fired a ball out the end. So we're going to start right here. Okay, and time is the x-axis, change in time, and the height is the y-axis. Okay. We're not going to put any numbers on it because that's not the point. It's to see what the shape of this situation is. So when you drop a ball from this height, it starts off falling somewhat slowly. And then because of the acceleration of gravity, it picks up speed. And again, this is very non-specific. Okay, you can just see that the space in between each of these is growing. Now I don't have enough space to put one more in, so we're just going to end it right there and make that our y-axis, or make that our x-axis where the height is 0. Okay, and then we shot a ball out of the spring cannon. And so what happened with it was it started in this same spot, and then after 1 second, let's just say it's 1 second, it ends up right over here. Okay, so 1 second passed and a ball fell that far, and it also shot that far, and they ended up at exactly the same height. Okay, and then it'll keep falling and moving forward. Something like this. At 2 seconds, notice that they are still at the same height. At 3 seconds, notice that they are still at the same height. At 4 seconds, notice that they are still at the same height. Okay. All that is different is that the fired ball has horizontal velocity. We would call that Vx. Okay. The dropped ball does not have any Vx. Vx equals 0 for the dropped ball. But for the fired ball, it has a horizontal velocity. Okay. It also has a vertical velocity. Okay, not at the beginning. At the very beginning when it's fired out of the spring cannon, it does not have vertical velocity, right? It picks up vertical velocity over time because of the acceleration of gravity. The same thing happens here. It does have an increasing vertical velocity, but it does not have any at the beginning. Both of these things would be considered in free fall, so they would be considered projectiles. Okay, a projectile is just any object that has only the force of gravity acting on it. So if you drop an object and it's in free fall, it only has the force of gravity acting on it, neglecting air resistance. And so that would be considered a projectile. Or if you would throw something forward, then it would also only have the force of gravity on it once you have let go. Okay, that's important, that a projectile has an initial force that caused it to start moving forward, but once you have let go of that thing, then you are no longer pushing it forward. Then there's nothing that's pushing it forward. It has horizontal velocity because of the initial force at the beginning. Okay, and we don't need to take that initial force into account anymore after it's in free fall. Some important things, we just discussed what a projectile was. You also need to know that trajectory is the path that the projectile follows. And so if it starts on the ground, let's say, its trajectory might be like that. If it starts from, let's say, the top of a cliff, its trajectory, I can say that word normally, would be something like that. But in both cases, they would be a parabola. Okay? The flight of anything in free fall is modeled by a quadratic function. In the case of something that starts from the ground and lands on the ground, it actually traces out a parabola. In the case of something that does not start from the ground but does land on the ground, this traces out half a parabola. Okay? You could also have a situation where something starts from the ground and ends not on the ground, in which case this is a portion of a parabola, but not the whole thing, obviously. So we can always use quadratic math in order to figure these things out. But there are other strategies that we're going to employ as well. You also need to know that the range, where in math is the set of y values you can find on a function, that's not what we're referring to here. The range is how far something travels. So it's actually, we're talking about how far has it moved in the x direction. Okay, so range, you could also label it displacement in the x direction. So try not to get that mixed up, especially if you're taking math at the same time right now. Now we're going to jump all the way to just doing some examples, because that's the best way of getting a sense of how all of this works. So an airplane is flying in a horizontal direction at 125 meters per second at an altitude of 1,250 meters. The airplane then drops a package. How fast is the package falling vertically when it strikes the ground? Okay, so I want to start off by just imagining something. Here's our airplane. Oh boy, here's me trying to draw again. There, I'll even give it wings. Perfect, right? So when this airplane is traveling horizontally like this, if you've ever played an old style like arcade game, there are certain arcade games where you're trying to drop an object onto a certain space. Okay, and so in those type of games, this airplane is flying and then it drops a package and the package drops straight down like this and the airplane continues flying. But that is not how physics works, because the object that's inside the airplane also has the velocity of the airplane when it drops. So I'm going to draw that object inside the airplane as well so we can visualize that. So it has a package. Let's say it's over here. There's the package. When the airplane is flying at 125 meters per second horizontally, the package is also flying at 125 meters per second horizontally. And so when it is dropped, when the doors are open, then suddenly gravity will start to accelerate it downward, but it has not stopped moving forward. Okay, so now its path is going to look something like this. It's going to form half of a parabola. Okay, and that's because it maintains its horizontal velocity. That just doesn't change. In reality, air resistance is going to decrease the horizontal velocity a little bit, especially when you're traveling that fast. But we're going to neglect air resistance for all of our projectile stuff. We can save that for a different time. So it's going to trace out a half parabola. It's got its horizontal velocity to begin with, and it starts with 0 vertical velocity, but then as gravity speeds it up, acceleration is 9.8 meters per second every second, then its vertical velocity will be catching up. Okay. Now, I want to point out that at the very bottom over here, it looks as though this projectile is moving straight downward, right? The way that I've drawn it, it looks like its velocity is perfectly downward at the end. And that's just not true at all. So at the very end, its vertical velocity is probably just a lot faster than its horizontal velocity. And so I should not have actually drawn it ending vertically like that. I should have drawn it ending slightly horizontally still. And so it would look more like this. Okay, and notice that it's not actually falling vertically to the ground at the end. It's falling like this, kind of at a diagonal. That's because it is still traveling 125 meters per second sideways, as well as whatever it's traveling downward. So we can show the components of this vector. I'm going to draw it a little bit bigger. Let's say like that. The components of this vector would be 125 meters per second sideways. That's Vx. And its Vy we could figure that out. Okay, and both of those things together give you the velocity at the end. You're going to do a lot of solving for what is the final velocity when this object hits the ground. So first, it's only asking us how fast is it falling vertically when it strikes the ground. It's not asking us for this total velocity over here. Okay, so this would be v, well, let's call it v2, the final velocity. It's not asking us for that. It's only asking us for the vertical velocity. It's asking us for v2y, just v2y. Okay, so it's asking us for the final velocity. That's why I called it v2. And it's only asking us for the y component of that vertical velocity, or sorry, of that final velocity. So that's why I called it v2y. Okay, so that's what we're being asked for. And then we should list the other things that we know. But we should only be listing the y things that we know. Okay, so the fact that it's moving 125 meters per second horizontally, that does not come into play here. We only need to take into account the vertical stuff. Okay, so I know that the altitude, the distance that this thing is going to fall, is 1,250 meters. And that's all it tells me. But I also know that the acceleration is 9.8 meters per second squared. And I know v1y is 0 meters per second. Okay, it's starting from rest. Only vertically though. It's not starting from rest. It's moving horizontally very, very fast, but it's not moving anywhere vertically until the doors open. Okay, so we need to make sure that we're only thinking vertically here. And so this d, we're also going to make it y. I don't need to label the acceleration the y acceleration because there is no x acceleration, and in fact there will never be x acceleration in a projectile situation. It's in free fall. There's nothing pushing it forward. So now I think to myself, what can I use what formula can I use these variables with to get me v2y? And when I look at my formula sheet, I can see v2 squared equals v1 squared plus 2ad matches what I have and what I'm looking for. Okay, and since I'm trying to solve for v2, I don't even have to rearrange this thing. Now, I could put y's on all of my variables here, but I know I'm doing a y calculation, so I'm not going to put it in all over the place. I am solving for v2 though, so I want to do the square root of v1 squared plus 2ad. And then I'm going to plug in my numbers and solve for v2, which gets me 157 meters per second down. Okay, that is my final y velocity. Okay, so I'm going to keep that in mind because it's going to ask me some other things about this now, and I might need that later. The second part asks us, how long will it take to hit the ground? So in this case, it's asking us for change in time. Okay, so the timer starts when the cargo bay doors open, and the timer stops once it touches the ground. Okay, so we're trying to solve for change in time, and we still have access to all of these things as well. Okay, now we don't really need to take into account anything horizontal still, because the time it takes to fall 1,250 meters, that's how much time it takes to travel whatever the distance is horizontally as well. So we don't really need to care about the horizontal part yet. We just need to know how long does it take for an object to fall 1,250 meters. That's it. And so we can use even our simplest formula. We can use v2 equals v1 plus a change in t, because that has time in it. We know v2 and v1 now. This is all y stuff we're doing again. There is no y acceleration, or there's no x acceleration, so we can just leave that as y acceleration. But I need to rearrange this now. So I end up with v2 minus v1 divided by a is equal to the time. Okay, and then I'm going to put my numbers in. So V2 is 157 meters per second, and V1 is 0. Okay, and this is where a lot of people kind of get things mixed all together, because it tells us that our initial velocity was 125 meters per second, I think it was, horizontally, but we're not doing anything horizontally right now. We're only dealing with vertical stuff. And so our V1y is 0 meters per second. And so we're going to divide that by 9.8 meters per second squared. Everything that we're doing is downward, and so I have just named down positive. Okay, so all of these values, they're all positive because they're all down. And so that gives us our change in time, which in this case is 16.0 seconds. That's how much time it takes an object to fall 1,250 meters, whether it's moving forward or not. Remember from our original demonstration with the spring launcher? It's going to take the same amount of time to hit the ground whether it's moving forward or just falling. So we don't need to take into account the forward motion in order to calculate how much time it takes to hit the ground. Let's see part 3. What is the actual velocity when the package hits the ground? So at this point we're looking for V2 total, X and Y together. Okay, and so when this package hits the ground, it's moving like this. Okay, it's not moving straight up and down, and so we need its horizontal velocity and we need its vertical velocity to figure out V2 total. So this is Vx and Vy, or V2x and V2y, and that gives us a total of V2. Now, I said V2x and V2y, but V2x and V1x are the same thing, right? Because there's no change in horizontal velocity. It's moving the same speed the whole time horizontally. And so we don't actually need to ever label it V2x and V1x because those values are always going to be the same in free fall projectile situations. So when I'm solving for V2, I'm going to use a squared plus b squared equals c squared. I'm just adding two vectors together. So V2 total is Vx squared plus V2y squared. And when I do that, I put in my 125 meters per second and square it. And I put in my 157 meters per second and I square that. And then when I square root it all, I get a final velocity of 201 meters per second. Okay, I need to give it a direction though, right? It's asking me for what's my actual velocity. It's not asking me for what's the speed when it hits the ground. If it was asking me for speed, I'd be done. But I need this angle. And I like drawing my triangles like this, drawing the horizontal velocity first and then the vertical velocity, because expressing the direction of that final vector is just easier that way. We can call it below horizontal. Okay, you could also say above vertical. If you wanted to draw your vector diagram like this, where this is V2y and this is Vx, this angle over here would be a certain number of degrees above down or above vertical, but it's just a little bit clunkier and more confusing in the language. So I would rather draw my Vx arrow first because I can say below horizontal as my direction then. Okay, there's no rule that says that you have to do it that way, but it's just probably a good idea. So now I'm going to figure out that angle by doing the inverse tan. So theta equals the inverse tan of Vy over Vx, right? Opposite over adjacent. And so when I do that, I'm doing the inverse tan of 157 over 125. And that gets me an angle of 51.5 degrees. And so my direction that I'm going to give here is 51.5 degrees below horizontal. And when I say below horizontal, everybody knows what I'm talking about, at least if you've heard that before. You don't have to figure out what does above vertical mean. That's really confusing sounding. So anyway, that's my vote. And the last thing that we're supposed to figure out is the horizontal displacement of the package. And if you recall, horizontal displacement is another way of saying range. What's the range of the package? Okay, so now we're supposed to figure out what is displacement in the x direction. Okay, and this last step, whenever you're asked for the range, it's always fairly straightforward. You need two things. You need the horizontal velocity. So we're looking at what's all the horizontal stuff that we know. We know Vx is 125, not 1 point anything, 125 meters per second. And there is no other x stuff that we know, except for one thing that doesn't have direction on it, and that's time. And we know that the time is 16 seconds. This looks like 125, but I really meant 16 seconds. Okay, those are the only pieces that we need to figure out the displacement, because we have this formula. Displacement equals velocity times change in time. Okay, this is really average velocity though, right? So that's one of the very first formulas you ever learned in physics. Average velocity times time is displacement, or you may have seen it like this: average velocity equals displacement divided by time. Okay, I just rearranged that thing. Because we know that the horizontal velocity does not change at all during this whole time, the horizontal velocity is average velocity. And so we can, in this average velocity spot, we can just put Vx there because it is an average velocity. It's a constant velocity. And so that's the way it works. So we can put that there. We already know that the time is 16 seconds. And so this calculation is a very straightforward one. We're just going to go 125 meters per second times 16 seconds. And that is how far it has traveled horizontally, which is 2,000 meters. Now, if you are really wanting to round that to the correct sig figs, that's not the correct sig figs, right? That's only one sig fig. So let's look back at the very beginning of the question and figure out how many should this be. Both of the values we're given have 3 significant figures to them. So our final answer here should have 3 significant figures. But I can't round this to 3 significant figures. So instead I just need to write it a different way. And so I can write it in 2 different ways. I can just say in brackets here 3 sig figs, like that. That's kind of the lazy way to do it, but it's valid. You're totally allowed to. Or you can instead go 2.00 times 10 to the 3 meters per second. That has the correct number of sig figs. Now, I am not really fussy about sig figs in this course. That's not one of our focuses, but it is a good rule of thumb for how to round your final answers.